Okay, so we're going to continue on from where we left off with strain gauges. And if you recall from last time, we had a problem when we had a small change in resistance trying to measure that. And bridge circuits are a common thing to use to measure changes, small changes in impedance. If you recall, the strain gauges convert strain into a change in resistance, and we were using numbers like 120 ohm is our base resistance, and the strain would add maybe 2 to 4 ohms on top of that. Just measuring resistance through normal techniques is not very convenient, and if we just try to put it in a voltage divider and things, we end up with large offsets and things like that. So we're going to turn to Wheatstone bridge circuits for strain gauges, and I'll point out too it. Anytime you're measuring a change in impedance, whether it's a DC resistance or a reactance or something like that, a bridge circuit is something good to consider. So what is a bridge circuit? It's a circuit that crosses a river, right? No, it's not. Let's draw a picture. We make a square circuit with resistors or other impedance elements. They don't have to all be resistors, because if you recall, Z is impedance, which is the complex, more generalized version of resistance. We apply our source voltage, constant voltage, and I'll also say there are some constant current bridges, but the math is slightly different, to the upper and lower points here and here. And then we measure the voltage, our output voltage, from these right and left points here. Okay? So what I've really got here is a keyboard that I can't see. There it is. If I were to divide this circuit in half, I have two voltage dividers, right? And I'm comparing the result of two voltage dividers. And each voltage divider, if I were to look at this voltage right here, is going to be equal to Z4 over, if I measure it relative to ground, to that point there, Z4 over Z2 plus Z4 times Vs. And if Z2 equals Z4, then my voltage at this point here relative to ground is going to be basically Vs over 2. And if I did the same thing on the other side, my voltage here relative to ground is Vs over 2. But the difference between these two voltages, when everything's equal and everything's balanced, my difference in voltages is 0. So I got a nice starting point where I can set this bridge up so that it's balanced and my no strain output is 0. And then as I change the impedance of one or more of these devices, my bridge will rebalance itself or unbalance itself, and I will get a voltage out here that is proportional to that change. So let's do the math, because we all love math, right? What is the relationship between Vs and Vs out isn't labeled here? Well, I can write down from Kirchhoff's voltage law, I can look at the voltage across the loop this way, and that gives me this equation here. The voltage source equals current through this leg 1 plus times Z1 plus that same current times Z4, so that's the voltage through that loop. I can look at the loop around the other side, and I come up with the same equation essentially. I can look at V out in terms of the difference between the voltage drop across Z3 and Z4, which is I2 times Z3 minus I1 times Z4. I can also look at it as the difference in the voltage drops across Z1 and Z2. There's a lot of ways I can rearrange this. That's that last equation. But what we're going to do here is essentially, if we think of it as two voltage dividers, one on each side, I have this voltage at A, and I have the voltage at C, and my output voltage is the difference of those two voltages. And the voltage at EA is our voltage divider equation again, where I have the total impedance, Z2 plus Z3, and I have the impedance here, the voltage across this bottom, so it's just essentially what fraction of the total impedance is that impedance times the source voltage. That gives me my voltage divider on the A side, voltage divider on the B side, and as long as everything's equal, Z1, Z, I shouldn't say they don't have to be equal, as long as the, we'll get to that. Jumping ahead. And I can recombine all those into this relatively ugly equation, but in practice a lot of these are constants, and ugly as it is, it works. And as long as the ratio between Z1 and Z4 on one side is the same as the ratio between Z2 and Z3 on the other side, the bridge is balanced. Our V0 is 0. I can rearrange this algebraically to get those ratios the same there. It's convenient typically to just make all of the resistors about the same, but there are sometimes times when you won't do that. So here's an example of using a bridge circuit with a device such as a strain gauge. So if we assume we have a strain gauge with a nominal resistance of 100 ohms, and when I strain it, I get a delta R of 2 ohms. My Vs is 5, so this is 100 plus 2 there, because I'm going to put that strain gauge in this Z1 position here, right there. Z2 through Z4 are replaced by resistors with R0. So this is 100, 100, 100. We should be able to calculate what the maximum output voltage is going to be when this is at 102 there. I'm going to defer that to the next slide because we're kind of go through the math there on the next slide a little bit. But what we'll do on this slide is answer the question, what is the maximum voltage supply I can use. If I go back one slide, I can see that my voltage output is a function of the voltage source. So the bigger my voltage, source voltage, the bigger my voltage output is for any change in resistance. So we want to say, if these strain gauges are good for 50 milliamps, what's the maximum voltage source I can use without essentially overheating them? Well, that one can apply good old-fashioned Ohm's law. We can say that Vs equals I, the current through our strain gauges, and we'll just look at one branch. Doesn't matter which branch. Well, I guess it does in this case because I only have a strain gauge in one branch. So we'll look at this branch here. The I through that left branch times the resistance in that left branch, and our I that we want maximum I is 50 milliamps, and our resistance is those two resistors in series. So it's basically, I'm just going to use 200 ohms for the nominal case because that's essentially worst case. So 0.05 times 200 gives us a Vs equals 10 volts maximum. So if I use a 10 volt supply here, I won't overcurrent my strain gauge, and that'll give me my maximum V output that I need. So let's run through the math for this situation where it can be either Z1 or Z3 is active. In this example, we're going to use Z1. So Z1 is R0 plus some delta R. All the other arms are at R0, R0, R0. And this is our strain gauge equation from a couple slides back where I substituted a little bit. Basically, this term here is Z1 times Z3. This term here is Z2 times Z4. And in the denominator, I have Z1 plus Z4 and Z2 plus Z3. And we just substitute all that in. Okay? And I wrote that in a bad place there. Okay. So we can kind of simplify that whole thing to this equation and couple more steps here. There we go. Sorry, my mouse was not cooperating. That's getting ugly there. But if I assume that delta R is a lot smaller than it's not writing. Okay. I may be done here. We may be dead in the water. It's not talking to me. Wimba is locked up. No, it's not completely locked up because the mouse is working, but not my touch screen. No, now it's working. Okay, so I got all that garbage. It's kind of ugly, but if I assume that the delta R is a lot smaller than R0, which in this case our delta R is 2 and our R0 is 100. So my term here, 2 delta R over R0, is actually equal to 0.04. The difference between 4 and 4.04 is small. We can do that small. We can approximate that and throw it away, and we get our final equation, which is a slight approximation, 1/4 times the voltage source times delta R over R0 is the equation that we'll work with to do our actual solution. Okay? So if the active arm is a strain gauge and delta R over R0 is our gauge factor times epsilon, the strain, then we come up with our voltage output as a function of epsilon or a function of our strain is 1/4 gauge factor source voltage, just like that. Okay, it works out nicely. It's fairly linear. It goes through 0. We can work with things like this. And if I just throw some numbers in here for the sake of entertainment, if my Vs equals 10, R0 equals 100, delta R equals 2, then I get a V0 equal to 0.05, and I didn't calculate what epsilon that corresponds to. I'm basically using this equation up here. But we'll get voltages. They're small, but they're linear, and I don't have the problem with them not passing through 0. I'm going to erase this. So how would one improve the sensitivity of the strain measurement? Well, obviously increasing Vs would help, but then we get potentially current problems. Another thing we can do is we can put two or more elements. If I put another strain gauge here operating the same way, I essentially unbalance both voltage dividers so I get twice the output, and we'll explore that. So if we have two arms active, they have the same size, sign, as in I have two strain gauges, both in tension or both in compression. So my impedance is R0 plus delta R, and the delta R is approximately the same in both of them. This would be an example where I have say a bar in tension. I can put a strain gauge on each side, and I get the average strain, essentially. So here's my equation, plugging all that stuff back in. So this was Z1, Z3, and this is Z2, Z4. That's just R0 squared because those haven't changed, and we said they're all the same. Z1 plus Z4, Z2 plus Z3, okay? We can chunk through the algebra, we get to that, and if you want to follow along, I'm not going to take the time. Stop the video, work it out yourself, and make sure it makes sense to you. Again, we can apply that same small delta R approximation that we had before. And now, for the same numbers I ran last time, I get, instead of a 0.05 volts, because this is now 1/2 instead of 1/4, I get 0.1 volt strain with the same conditions as last time. So I've doubled my gain. And then we also change our equation here as a function of the gauge factor and epsilon. This 4 has gone to a 2. So I've got twice the gain here because I'm using two strain gauges in opposite legs. And I can do things. If my beam is in bending, for example, I'm going to get one strain gauge in tension, one strain gauge in compression. I put those on the same leg, okay? And there's the equation. Again, I'm not going to run through it. I've got the same gain of 1/2 here because I have two strain gauges working together. And again, this is the same 1/2. And the other question is, how do temperature changes cause additional strains? Remember, we talked about these being sensitive to temperature, particularly when you use semiconductor things. Well, if the temperature raises the impedance here and raises the impedance here, that pretty much cancels out. So let's take a look at the math. So, we'll get to that in the next slide. Okay, I'm one slide ahead of myself. Here I have a case where I have my beam in bending again, Stratton bending, and I have strain gauge, and I can probably put two strain gauges somehow side by side, close proximity. Now I have strain gauges in all four corners. Two of them will be in tension, and two of them in compression. That's a C, not a, okay? Arrange it like that. Now I've got the plus and minus delta R's everywhere you want to go. Click. So now instead of being 1/4 or 1/2 here, I have a straight up, the V out equals Vs times the delta R over R0. So I've got a gain that is 4 times the gain of the single active strain gauge part. And there it is in this form, same thing. So again, how do those temperature-induced strains affect the output voltage in this configuration? Pretty much they don't. But let's just look at one. I'll go back to our original case where we have one active strain gauge right here. We'll say this one's in tension. And I've got a dummy strain gauge right here that's just sitting somewhere neutral but nearby. For Z1, my impedance Z1 is R0 plus delta R due to the strain plus delta R due to temperature, right? And at Z4, that impedance is R0 plus the delta R just due to temperature. And if we make our usual assumptions about all the other resistors being equal, again, stop the video, work out the math if you want. You know, it's just a matter of chunking in the algebra. And what I get is all of those delta RTs cancel out, okay? Pretty much. You know, there's still this 4 delta RT R0 term, but if delta RT is small compared to R0, and it will be, and delta RS is small compared to R0, that cleans up our denominator terms here. And then that gives us essentially the same equation here, and the temperature effects have, for all practical purposes, gone away. Okay? And of course, we have the same equation here that we had all along. Of course, if we're using all 4 strain gauges as strain gauges, you get much the same effect, because the increase in impedance here matches the increase in impedance there, increase in impedance there matches the increase in impedance there, and our balance, you know, the ratio between those doesn't change much. It does a little bit, but not much, you know, given the fact that delta RT is small compared to R0. Now, if we had perfect components, that's all we need to do, right? If I just said, I'll make this 120 ohms, this is 120 ohms, this is 120, and then the thermal effects, and this is 120 plus delta R due to tension, that's fine. But they're never perfect. So usually what we'll include is some way to tweak things up and balance the bridge to account for it. We can put a resistor here in series. We can take one of these points and put it on the adjustable arm of a potentiometer to kind of move it up and down a little bit. We can put a resistance in parallel. You can actually even kind of put a bias voltage at this point here if necessary. And all of these things you would start off by sitting with the bridge in its nominal case and adjusting those so that you get 0 voltage across your output points. And when that happens, you know, you have one of these balance conditions, and they're both sets of equations are algebraically equivalent. Okay, and there's our equation for a balanced bridge where, yeah, you do the math. Now, the other thing we need to do is we need to calibrate the bridge to know that a certain strain based on our gauge factor is going to result in a certain output, and we want to calibrate it and measure it and make sure that that whatever circuitry we have out here is giving us what we think we have, because there's going to be imperfections in any amplifiers that we're going to use here. The gain may not be exactly what we think the gain should be. Most likely what I'll do is I'll put this into, I'm running out of room. Let me move this over here. Put a resistor there, put that into an op-amp circuit. But the gain in those resistors aren't going to be exactly what I think they're going to be. So we got to do something to calibrate this bridge from end to end. And one of the things we can do is put in, we can balance the bridge with just our strain gauges in here as necessary. And then I can have this resistor here we're calling RC, or sub C, that will change the resistance of this whole leg such that R0, our nominal resistance, minus the delta R cal, the change in resistance we want to calibrate for. That delta R cal is going to correspond to some particular strain that we want to calibrate for. And we got to calculate what the parallel resistance value of RC is going to give you, is going to result in the same effect as if we had actually changed that resistance here in that strain gauge by straining it. And it's a minus because I can't put a resistor in parallel and make it a higher resistance. We can only calibrate in one direction. But so if I take my equation for a parallel resistor here, I'm going to let this term here equal X just to save some work or save some writing. I can rearrange that to say that, well, I'm not going to do that. I'm going to do that on the next slide. Yeah, let's do that on the next slide because that's exactly what the next slide asks us to do. So if I want to calibrate a bridge circuit, what should the calibration resistance be to simulate the output of a single active arm bridge with a strain of 0.02 inches per inch, gauge factor is 2.2, and R0 equals 100, okay? So the first thing I want to do here is calculate for any given delta R, what is my calibration resistor. So my equation here is R0 minus delta Rx, or RCal, excuse me. This is our calibration delta that we want to hit, equals RC R0 over RC plus R0. Oh, excuse me. That's just our the parallel equivalent of those two resistors, that change in resistance. So, and again, I'm going to make this equal to X for the simplicity. I can rearrange that XRC plus XR0 equals RC R0. I just brought this over. And again, if I make a leap of algebra that you're not following, just pause and work it out and tell me where I made my mistake. I can rearrange, clean that up a little bit, and I get RC equals XR0 over R0 minus X. And since X equals R0 minus delta RCal, I can put it back in here. I'm going to write this at the top because we're going to come back to this. RC equals R0 plus delta RCal times R0 all over delta RCal. Okay? Now the next part of it, I'm going to erase this. Need a bigger eraser. The next part of it is what value of delta RCal do I need, right? I have a strain, I have a gauge factor. So I know that from my strain gauge equation that delta R over R equals my gauge factor, GF, times strain epsilon. So rearranging that, delta R equals 2.2, our gauge factor, times 0.02, our strain, times 100, our nominal resistance, and I get a delta R equals 4.4. So if I have a delta R of 4.4, I can plug it into this equation up here, and I get RC equals 100 plus 4.4 times 100, I guess I didn't need those parentheses, divided by 4.4, and I get RC equals to 2.17 K ohms. Okay? Pretty straightforward. Just a matter of chunking out the algebra. And we can take the same concepts and do them backwards. In the other case, or in this case, we suppose that R0 equals 120 ohms. Our gauge factor is 2.1 over here. What is the equivalent strain if the calibration resistance equals 100K? So in this case, we're given a calibration resistance and we want to work backwards to the strain. So if I go back to my equation for the parallel resistors, R0 minus delta R cal equals RC R0 over RC plus R0. I know everything except delta R cal, so I solve for delta R cal equals R0 minus RC R0 over RC plus R0. And if I plug in the numbers of 100 kilo ohms and 120 ohms, and assuming I didn't make any mistakes, I come up with 0.144 ohms for our delta R cal. And remember that delta R over R equals gauge factor times epsilon. And substituting, I've got delta R, I've got gauge factor. I want to solve for epsilon. And so delta R over R times gauge factor in the denominator here equals epsilon, so that's 0.144 over 120 times 2.1, and that should come out to be 5.7 times 10 to the minus fourth in terms of our strain. And that wraps us up. There's some examples of using one, and I'll do one more video on some examples where we use bridge circuits for impedances other than strain gauges or other than just straight resistance things. But catch you next time. Bye.